So our next speaker is Hubie Chen from Universidad, País, Vasco, and he'll tell us about the logic of counting query answers.
Thanks. So I'd like to thank all of the everyone involved with the organization of this workshop and this program for the opportunity to participate and to speak. Today I'll talk about joint work with Stefan Mengel, who's working in France. Okay, so I want to just begin with an overview. The initial computational problem that we'll be concerned with in this talk is sometimes called query evaluation. And we just want to evaluate a formula on a finite structure. So we want to determine, given a formula and a finite structure, the set of assignments that satisfy the formula over the structure. And throughout the talk, I'll use this notation phi of b to note this set of assignments. In this talk, phi will always be a first-order formula. And in fact, we're going to focus on the counting version of this problem, which is to determine the number of answers. Again, given these two things, a formula and a structure. Okay, this is intractable in general. So just to give a concrete example, the formula is something that might look like this. So in this problem, we'd be given a formula, a structure, which interprets the relation symbols. And we want to count the number of assignments to the free variables of the formula that satisfy the formula and the structure. Okay, so this generalizes the model checking problem, which here I define to be the problem of deciding if a sentence is satisfied by a structure. For we have that, well, the empty assignment satisfies a formula, if and only if, sorry, a sentence, if and only if, is an answer to a sentence, if and only if the sentence is true over the sentence is true on the structure. Okay, so let's suppose that we have a first-order formula in our hands, and we're sort of interested in counting the number of answers over maybe various databases or structures B. Sort of the motivating question for this talk, which I'll elaborate on as we go, is whether or not there's sort of a good language or logic in which we could express useful algorithms for computing the mapping, which takes us from a structure to the number of answers for this first-order formula of interest. And in this talk, we present such a logic, which we call sharp logic. And sort of one application that we envision is that it could serve as a target language into which one could compile first-order formulas of interest. And I'll elaborate this sort of, again, more as we go. But we sort of, our logic will enjoy and balance two properties. On the one hand, it'll be sufficiently expressive to allow for the direct expression of efficient algorithms for this counting problem. But on the other hand, it'll enjoy a good computability problem, namely minimizing a quantity called width we can do computably. Okay, so now I want to say something about the background for this talk. Okay, so the counting query answers problem is intractable in general. It's well known that if we just restrict a problem to a single first-order formula, the problem is tractable. And one of the things that we wanted to do in this work is to try to identify types of formulas which enjoy good computational behavior, tractable behavior. And in the literature, there's a established way of sort of restricting the general problem to try to study sort of which formulas are well behaved. Namely, we restrict the general problem to a class of formulas. So for every single class of first-order formulas, I'll define our counting problem over phi to be this restricted version of the general problem where the formula must come from our class, right? So now again, we're just given a formula and a structure, but the formula has to come from this particular class. And we want to perform the count. Okay, so yeah, so for example, we might ask for which classes of first-order formulas is this problem tractable and for which is it not?
So can I just ask a question? Because you said you're talking about model checking, but now if the formula is part of the input, it's and first order, of course, is a zero, but if the formula is part of the input, it's piecewise complete. So I'm not sure which one you're looking at.
So here,
if the formula is part of the input?
Yeah, the formula is part of the input.
Okay. So typically that's going to be piecewise complete, even for a really weak language, right?
Well, it depends on the particular class phi, right?
Okay.
I restrict the general problem according to some class phi.
Okay.
Right. So
you restrict to a single first-order formula, where you don't get
yeah. So I just
you don't understand.
Sorry, what's this?
So this capital phi could be a singleton, and then it's easy.
Yes.
Exactly, right?
Then the complexity is tractable even for counting. That's what it is. Yeah, if the formula is fixed, yeah. It's in log space.
Right. This is a way of sort of interpolating between these two extremes, right? The general case is where we take the class of all formulas. This is saying, well, if we take just a class with one formula, we get polynomial time tractability. And so this is a way of sort of exploring the space in between, perhaps.
Okay.
Okay, so, well, it's been argued repeatedly in the literature that classical complexity theoretic notions like that of polynomial time aren't totally satisfactory in the study of query evaluation. For a typical scenario is the evaluation of a small query or formula on a big structured database. And this sort of discrepancy between the two parts of the input, this asymmetry, suggests that maybe we could tolerate a bad dependence on the query or formula as long as we have a good dependence on the structure. And so there's a sort of suitable complexity theoretic framework for studying precisely this type of situation, parameterized complexity theory, where essentially we classify problems up to allowing arbitrary computation on a parameter. I'll be a bit more precise in a moment. Okay, we always take the query or the formula to be the parameter, so following this motivation. Okay, so again, this is our sort of family of problems. For every class of formulas, we have a counting problem over phi. We want to maybe understand which ones are tractable and which ones are intractable. And the particular notion of tractability we use is fixed parameter tractability. So here's a formulation. We relax the notion of polynomial time to allow a preprocessing in the formula, right? A computable preprocessing. So we say that there just has to be some algorithm f that's allowed to preprocess the formula, but then sort of after that preprocessing, in polynomial time, we can compute the desired value.
So f of phi could be arbitrarily big after the preprocessing.
Right, in particular, f of phi can just blow up the formula exponentially or worse, right? So again, we relax the notion of polynomial time, but just allowing this preprocessing only on the parameter, which is the formula. Okay, so in recent work with Stefan, we classified all existential positive formulas. I'll use this notation just to indicate that we restrict first order logic according to these connectives. So for any class of existential positive formulas of bounded arity, we prove a dichotomy theorem. We show that if some condition holds, which I'm not going to describe here, then the counting problem is tractable in the sense that I just described. And otherwise, we prove that the counting problem is not tractable unless an unexpected collapse occurs in parameterized complexity theory. And so this gives sort of a full dichotomy theorem for, at least for existential positive formulas. Okay, now I want to talk about width. So I think we've seen this already this week, but the width of a first order formula is the maximum number of free variables, overall subformulas of the formula. It's a syntactic measure of a formula, maybe sort of a syntactic measure of complexity. And there's a sort of classic observation that if we restrict model checking to formulas of bounded width or bounded number of variables, then in fact it's still in polynomial time, right? So if we impose a bound k, then model checking a sentence of width at most k on a finite structure is polynomial time tractable. Right? You just sort of do the naive inductive evaluation. Okay, so just as a consequence of this observation, we can make another observation, which is that we get very easily a sufficient condition for model checking to be inside FBT. Right now we can relax this. We say, well, if we have this sort of compilation algorithm f that passes from every single sentence in our class to a logically equivalent sentence of bounded width, then this is going to be tractable in the sense of parameterized complexity, right? So again, we just sort of relax this condition. Instead of bounded width, we say, well, if we can computably pass to sentences of bounded width, then we're also tractable in the sense of parameterized complexity. Okay, so this was our observation. And in past work, we proved that for any class of existential positive sentences, if model checking is tractable on the class, then this sufficient condition for tractability is in fact necessary. So this sufficient condition is sort of the only possible explanation for fixed parameter tractability in this particular context. Okay, so here I want to highlight perhaps a conceptual point, which is that, like in our view, here first order logic is like playing the role of a useful model of computation, right? If we have tractability at all, we have tractability just by sort of rewriting the sentences and putting them into a good format, right? So like maybe another way we might think of this is that first order logic, in some sense, sort of modulo this rewriting, contains the computational primitives that we need to express these, the algorithms which witness tractability.
Can I ask a question here?
Sure.
Because this looks a lot to me like first order and fixed point, which of course has a bounded width, and in some sense you can either uniformly compute that formula using fixed point, or you're allowed to do it non-uniformly. So you're having more power than fixed point, but is that really needed? Do you need the non-uniformity? Otherwise,
what do you mean by non-uniformity here?
The non-uniformity is going to f of phi from phi. Right.
So what? Sorry, what's?
So my question is, okay, I want to compare your approach to first order plus least fixed point.
Okay.
Which is already a model.
It doesn't have a formula for every input size. It's one formula. It's one formula.
We have a class of formulas, right?
Coming from a class.
Okay.
We have an entire class. Think of it as a large infinite class of formulas.
You do the f of phi once, and then.
And we're saying that well, we have this sort of this algorithm f that for any formula or any sentence in our class can rewrite it into a bounded variable sentence.
Right.
But
that one sentence for all structure sizes?
Yes. Yeah.
Because I thought that
Everything's first order here, right? All sentences are first order.
But I thought you were using the kind of thing that k variable data logs suffices for this question.
This is like counting the number of triangles. You have one sentence.
Okay, I apologize. Okay, I'll shut up now. Sorry.
Right, so in fact, I could say here that, like in some sense, logic is playing two perhaps complementary roles, right? On the one hand, the computational problems that we're interested in are phrased directly in terms of logic. But on the other hand, somehow the algorithmic solutions to these problems that we're looking at also seem to be phrased in terms of logic, sort of in terms of this rewriting of sentences. Okay, so the motivating question for the present work is the following. We wanted to know if there was some sort of analogously useful logic for accounting query answers in which we could sort of express the efficient algorithms given by our dichotomy theorem, right? So in a certain sense, what we're asking for is some sort of counting analog of bounded width or bounded variable logic which retains sort of the good properties that we just discussed. And okay, just to be like completely clear about this, just recall that in model checking we have a sentence and a structure. We want to decide if the sentence is true on the structure. Of course, this is a propositional value, right? It's yes or no. In the counting answers question, we're given a formula and a structure, and we want to compute the number of assignments that satisfy the formula and the structure, right? So this is a numerical value, right? So sort of one criterion for our logic is that we should have some notion of sentence where when we evaluate it on a structure, it's going to give us a numerical value and not merely a propositional value. Okay, so we're going to give such a logic, which we call sharp logic. Okay, so let me say some things about the properties that our logic has. Okay, every single formula is going to have a set of free variables. If there are no free variables, we call a formula a sentence. And sort of maybe the first most relevant property is that once again, if we bound the width inside our new logic, which I haven't defined yet, but it's going to be the case that if we bound the width, then we still have that evaluation can be done in polynomial time, right? And sort of the sufficient, we can now come up with a sufficient condition for FPT as well, sort of analogous to our sufficient condition for model checking. And for this, we need this definition, which sort of links our logic to the counting query answers question. We'll say that a sentence in our logic, psi, represents a first order formula phi, if sort of psi sort of always tells us what happens, right? So psi is always going to tell us, when evaluated on B, it's going to give us this value, the number of answers to phi. All right, and then sort of, just as before, we get a sufficient condition for fixed parameter tractability, right? Now we say, well, if there's some algorithm which passes from every single formula to a sharp representation in our logic with bounded width, then the problem will be an FPT, right? And sort of the reason for this is just as before, well, you just apply this algorithm as sort of the compilation, and then you invoke this observation, which will evaluate the resulting bounded width sentence in polynomial time. Okay, so one of our main theorems is this. I showed this dichotomy theorem for existential positive formulas, and we proved that on these classes, this condition is the exclusive explanation for intractability and parameterized complexity. So if we have tractability at all, according to our dichotomy theorem, we have tractability via this sufficient condition. Or put differently, this sufficient condition is in fact necessary, at least for problems of this form. Okay.
But you haven't told us what the logic is yet.
Yeah, I'm going to do that, or I'm going to do that via an example here. So here, let's look at a little example, a tiny example. We have a formula just with two atomic formulas, V, Y, V, Z, and we have relations E and F. And sort of the first thing we can do in this logic is what we just, what happened? Yeah, so the first thing that we can do in this logic is what we call casting, which means that we just apply C to some first order formula, and we get a formula in our logic. And okay, let's let B be a structure. Now to specify the semantics of our logic, we have to say for every single structure and every single formula, and then every single assignment to the free variables, what the semantics are, right, which is going to be a number. And so when we cast a formula, we just get 1 or 0, depending on whether or not the structure and the assignment satisfy the casted formula. Now we have an sort of a quantifier, which we call projection. And okay, in this particular example, projection will behave like this. If we take this previous formula and we project away the variable y, and then we evaluate this on an assignment to v, we get the number of extensions of v, of this assignment, the number of extensions to y, which satisfies E of Vy, right? So again, this just says that, well, we fix a value for v, this is going to tell us the number of extensions which satisfy sort of this left part of the formula. Okay, now we can sort of do this for the other atomic formula. If we sort of project away the other casted version, we get the number of extensions for an assignment to v. We get the number of extensions which satisfy sort of this right-hand part of the formula, right? And now, okay, our logic has a multiplication, which just has the semantics that you think it has. It just will multiply the values of the previous two quantities. And if you actually think about it, this is going to be precisely the number of extensions to all of the free variables that satisfy phi, right? Because if we sort of fix a value for v, the other two variables, intuitively, they behave orthogonally, right? There's no constraint or interaction between them, right? So sort of with this, if we just project away the remaining variable v, we get a representation of phi, right? Which sort of always tells us the number of answers, right? Now, this was a small example, but actually this formula has width 2. The naive representation here will have width 3. And it turns out that, in fact, if we had an instance that looked like a tree, we could sort of apply this idea inductively, and no matter what the tree looked like, also get a representation of width 2. And then we can generalize this and say that, well, if we had a graph which had bounded tree, or which had tree width k, we can in fact cook up a representation sort of using similar ideas of with k plus 1. Okay, so this is just a very quick summary of our logic. We have this casting, which we saw. We have projection. We can expand the number of free variables. We have multiplication and addition. And we also allow sort of constants. We assume that they're cooked in to the logic, all integers, in fact. Okay, now I want to talk about width minimization. So let's imagine that we have some first order formula with these 3 free variables, a, b, and c. And let's define a new formula just by sort of shuffling around the free variables. Now, of course, in general, these two formulas are not going to be logically equivalent. But what is going to be true is that they're always going to be counting equivalent in the sense that they're always going to return the same number of answers when we evaluate them on any finite structure. Right? So we say that two formulas are counting equivalent if this holds. Right? We always get the same number of answers. So we're able to exactly characterize counting equivalence in primitive positive logic. So sort of without disjunction, just conjunction and existential quantification. And essentially what we prove is that sort of this renaming of variables and logical equivalence are the only possible phenomena behind counting equivalence. And this characterization, in fact, implies that it's computable to decide if two primitive positive formulas are counting equivalent. Okay, so we're able to prove this theorem, which gives sort of a good computability property of our logic. We call this width minimization. And this says that there's some algorithm which, given any formula in our logic where we only cast existential positive logic, outputs a logically equivalent formula which has minimum width. Right? So here's maybe like a rough idea of how the algorithm works. Basically, first we take each formula and we normalize it so that basically it's the weighted sum of primitive positive queries. In fact, we do this using the inclusion-exclusion principle. And okay, then we can sort of assume that the psi i's are counting inequivalent by applying the algorithm of the previous slide. And then what we do is we just sort of minimize each of these primitive positive formulas individually. But in order to justify this, we have to somehow show that all these primitive positive formulas really are orthogonal to each other, that they don't sort of cancel out. And so we prove sort of what we call the independence theorem, which basically says that if we have a non-trivial linear combination of primitive positive formulas like this, then we can always cook up a finite structure such that this linear combination doesn't cancel out to zero uniformly. Right? So there's always some finite structure on which this combination will evaluate to a non-zero value. And okay, I'm going to skip the idea of the proof perhaps, but yeah, I can discuss a consequence of this theorem. So let's just look at structures over some signature tau. And for a given structure A, let's take the vector where we have an entry for every single finite structure and maps a structure B to the number of homomorphisms from A. Right? Now our theorem, this independence theorem, implies, like via the Chandra-Merlin correspondence, that if we have like any finite sequence of pairwise non-isomorphic structures, then in fact if we take these vectors, they're going to be linearly independent. Right? So they really behave orthogonally from each other. And sort of as an immediate corollary, we obtain that like two of these vectors are going to be equal if and only if the original structures are equal. So these vectors really characterize the original structures. And in fact, this gives us an exact dual to a classical theorem of Lobos. Lobos sort of studied exactly the dual vector. So he said, well, take a structure B and let's look at the vector which maps the structure A to the number of homomorphisms to B. Right? So this is just the exact dual. And he proved sort of just a dual of this corollary. So sort of two of his vectors are equivalent if and only if the original two structures are isomorphic. Okay, so now I want to wrap up. Logics with counting mechanisms have been previously considered in a variety of areas. And one example is the counting logic studied by Immermann and Lander and subsequently by many others. And to my understanding, a typical motivation in these areas is the desire to extend first-order logic or some logic to try to capture properties that were not originally expressible. In this work, our motivation is perhaps somewhat different. We wanted to try to come up with simple logics that allowed for the direct expression of efficient algorithms for this counting problem. And once again, our logics sort of balance out two properties. On the one hand, we show that we could, in fact, express sort of the class of algorithms that we wanted to. But on the other hand, we showed this sort of good computability problem that we could computably perform with minimization. And indeed, this isn't a property that we should take for granted, as in positive first-order logic, with minimization is not computable. Okay, so I'd like to wrap up just by naming a couple of open issues. One is that we'd like to perhaps try to understand better expressibility in our logic. So one can ask if there are Ehrenfeucht-Fraissé style games for characterizing expressibility in our logic. And finally, in this work, we focused mostly on existential positive formulas. And sort of one can extend to larger logics, right? So one can try to, for example, prove classification theorems for larger fragments of first-order logics, or indeed for other logics. Thank you very much.
Thank you. questions? Janos?
I'm just confused. Can you give an example where you can count but not list?
Right, so if the number of free variables is huge, or say linear, the number of satisfying assignments could be exponential in the size of the formula, right? So I guess one has to maybe specify what one means by list.
No, but how can you say there are 5 without finding them?
Imagine that I give you the uniformly true formula with n free variables, right? So in a structure of size 2, there will be 2 to the n satisfying assignments, right? It's easy to compute 2 to the n given 2 and n, right? But to actually list them would take exponential time in n.
But you're asking polynomial delay? What kind of
listing? You have to specify the model.
Delay or cumulative polynomial?
In general, conceptually, I try to figure out what it means that you can say there are 5 people in this room who voted for Trump without
Are there?
without seeing them, without the algorithm having to visit them.
Well, the counterexample he's giving is when the number is just very big. I don't know that he has an example in mind when the number is small.
I don't know if it's satisfactory, but I think there are results in the Sheffer's dichotomy version where people have looked at the complexity of counting. I think Herman Kreinu had there, right? And there the only tractable case is the affine case, right?
Oh, right.
But
sure.
there are also, so if you, Sheffer's dichotomy for counting, the only tractable case is when you have systems of linear equations. This is a theorem of Kreinu and Herman. But when you look, also Kreinu with Brad have looked at enumeration for polynomial delay, and there I think it goes differently. I think it's only the Horn, the dual Horn that has. Do you remember that?
In fact, most of the tractable cases go through.
So it's different. There's an example where polynomial delay differs from counting. That's all I'm saying. I don't know.
Actually, I can comment that here I guess it's also different because like the counting, you just want to produce one number, right? So in fact, if you sort of dig into our proof, there are sort of like algebraic cancellations. So it might be easy to sort of generate the number, but hard to actually list all of the solutions.
Oh, I can imagine this, but do you have an example there?
Maybe I'll get back to you on that, yeah.
So I guess a possibly similar question is you mentioned using inclusion-exclusion at some point.
Right.
If that's really needed, then I think it answers Janusz's question because when you use inclusion-exclusion, you're really taking advantage of the counting rather than making lists.
Yeah, in fact, studying that is how I guess one could generate.
The question is it really needed? Could you have lived without inclusion-exclusion?
Right, thank you very much.